Hello everybody, it's your friend Daniel here and welcome back to another tuition video where in this video we're going to be covering the 2018 GCSE Physics Higher Tier Paper 2. And without any further ado, let's jump straight in. Starting off with question 1. A child drops a ball. The ball hits the ground and bounces. Figure 1 shows the velocity time graph for the ball. Air resistance has been ignored, and we can see the graph with velocity increasing, it suddenly turned into negative, and then velocity going back to 0. And we're meant to describe the motion of the ball between points A and B on figure 1. And the ball is accelerating uniformly. And you can see this because there's a straight gradient on the velocity time graph, and a straight gradient on the velocity time graph means the ball is accelerating uniformly, with a curved gradient indicating that it's accelerating ununiformly, and just like a horizontal line indicating that it's not accelerating at all. Then ask what direction is the ball moving between points C and D, and the ball is moving upwards. Now then, moving on to 1.3, the ball and the Earth form a system. What is meant by a system? And the system is a group of objects that interact. You would have quite often heard of it as a closed system, which means energy cannot leave or enter the system. Now, moving on to question 1.4. When the ball hits the ground, energy is transferred from the ball to the Earth. Explain how the data in figure 1 shows this energy transfer. And this is due to the speed of the ball after the bounce is less than the speed before. As you can see, before the bounce, the magnitude of the speed was 7 meters per second. And after the bounce, the magnitude of the speed is 5 meters per second. With this showing that the ball has lost kinetic energy. And since the total energy of both the ball and the Earth is constant, the kinetic energy must have gone somewhere, which means the kinetic energy must have been transferred from the ball to the Earth. You could argue it was lost in air resistance, but that would show a more gradual decrease, and the actual question says air resistance has been ignored. Now moving on to question 2. A student carried out an investigation to determine the spring constant of a spring, and then we're shown their data. Describe a method the student could have used to obtain the data given in table 1. Your answer should include any cause for inaccuracy in the data, and you may include a labeled diagram. I have decided not to, I've just decided to explain it all, but you would get marks if instead of explaining it, you've just drew the setup that I explained. And like I said, firstly, you set up a clamp and hang a spring from the clamp, and then using a second clamp and clamp stand, set up a meter ruler alongside the spring, making sure it's vertical to avoid inaccuracy, just getting the marks for identifying causes of inaccuracy, and then record the meter ruler reading that is level with the bottom of the spring, making sure your eye is level with the bottom of the spring to avoid parallax error. Then hang a 2 Newton mass from the bottom of the spring, or 2 Newton weight actually, hang a 2 Newton weight from the bottom of the spring and record the new position of the spring using this reading to calculate the extension of the spring. Then take repeats increasing the weights 2 Newtons at a time until you reach 10 Newtons for each weight with you calculating extension. And then we're asked why the student measured the investigation for 5 different forces rather than just measuring the extension of one force. And this is to reduce the effect of random errors. And then we're shown some of the data obtained by the student, and we're asked to plot the data and draw a line of best fit. Obviously, you just put the data on as I've done, and you'd use a ruler to draw your line of best fit, but I don't have a ruler on this PDF editor, so it will have to do. But yeah, you get the idea. And then we're asked to write down the equation that links extension, force, and spring constant, which you will have in your formula booklet. However, in 2018 they didn't have formula booklets. You guys are lucky. And then we're asked to calculate the spring constant of the spring that the student used. And what you can do here is you can just take any force and any extension and then just do it. I've done 10 and 20. So the force is 10 newtons and the extension was 20 centimeters because it wants it in newtons per meter. You change 20 centimeters into 0.2 meters. 10 equals k times 0.2. K equals 10 over 0.2, also known as 15 newtons per meter. And then we're asked for 2.6 to explain how the data supports the student's conclusion that the spring follows Hooke's law. And this is due to the fact that the line is straight, well, it's meant to be if you use the ruler, and it passes directly through the origin. And if you've well acquainted with GCSE maths, you'll know that that's the requirements for something to be directly proportional, for it to be straight and go direct, for it to be a straight line and for it to go through the origin. And then for question 3, P waves and S waves are two types of seismic waves created by earthquakes. Which one of the statements about P waves and S waves are correct? And it's that P waves are longitudinal and S waves are transverse. This is just something you need to remember. Most people will remember they're different, which just straight away eliminates these two options. So like worst case scenario, it's a 50-50 chance, but just try and remember that P waves are longitudinal and S waves are transverse. And then we're shown seismometers on the Earth's surface record the vibrations caused by seismic waves. We're shown the vibration caused by one P wave, and we're asked to calculate the frequency shown in figure 3. This, I believe, shouldn't be worth 1 mark, because what you have to do is you have to know that there are 4 wavelengths in 10 seconds, which leads to a period of 1.25 seconds, if you just count in each wavelength. And then you'll need to remember that frequency is equal to 1 over wavelength, and you get a frequency of 0.4 hertz. And I believe that's just a bit hard for 1 mark, because you need to count things, you need to understand how wavelengths are, how they look on a P wave, and then you actually need to calculate the frequency of it. Now, moving on to 3.3. Write down the equation which links frequency, wavelength, and speed. And as you can just use your formula book to get wave speed equals frequency times wavelength. And then for 3.4, the P wave, shown in figure 3, which is this figure, is traveling at 7,200 meters per second. Calculate the wavelength of the P wave. And what we need to do is we just need to use the formula which we wrote down for 3.3. 7,200 equals 0.4 times wavelength. Therefore, the wavelength equals 7,200 over 0.4 equals 18,000. And then for 3.5, we're asked to explain why the study of seismic waves provides evidence for the structure of the Earth's core. And this is because S waves cannot travel through a liquid, and they don't travel through the outer core, therefore giving evidence that the Earth's outer core is liquid. In 3.6, we're shown a simple seismometer made by a student, and we're asked why does the movement of the bar magnet induce a potential difference across the coil? And this is via the generator effect as the magnetic field around the coil changes. And then for 3.7, why is this induced potential difference alternating? And that's because the magnet changes direction. It goes, let's say for example, it goes down, which causes a positive potential difference, and then it goes up, which causes a negative potential difference. And then for 3.8, figure 5 shows how the potential difference induced across the coil varies after the bar magnet has been released. And we're asked what statement describes the movement of the magnet when the induced potential difference is 0. And when it's 0, it's stationary, and this is because the magnet moving is what causes a potential difference, so when it's not moving, there would be no induced potential difference. And for 3.9, the seismometer cannot detect small vibrations, suggest 2 changes to the design of the seismometer, which would make it more sensitive to small vibrations. And what we're asking to do is we're being asked to make the induced potential difference larger. And 2 ways we can do that is by increasing the strength of the magnetic field by having a stronger bar magnet, or number 2, have more turns on the coil, both of which would increase the induced potential difference as the bar magnet goes through it. Now for question 4, we're shown an unusually shaped container, and we're just asked to complete figure 6 to show the height of the water in all the tubes. You may have done this in an experiment. It's not a required practical, but many teachers like to do it, and you just have to know that all the water levels are equal. And then for 4.2, we're asked to explain why the further a swimmer dives below the surface of the sea, the greater the pressure is on the swimmer. And this is due to increasing depth, increases the mass of the water above the swimmer, increasing the force of the area acting upon the swimmer. Now for 4.3, I think this is a bit of a tricky question. Like, it's hard to explain it using just GCSE physics knowledge. if you have knowledge beyond GCSE physics, it's really easy to explain it in those terms. But other than that, I believe it's a bit hard, so I'm just going to try and do it. A person swims from a depth of 0.5 meters to a depth of 1.7 meters. The density of the water is 1030 kilograms per meter cubed, and the gravitational field strength is 9.8 newtons per kilogram. Calculate the increase in pressure on the swimmer, and we're asked to give the unit. So what it is, I'm just going to make it larger so we can see all the maths, is the increase in depth from 0.5 to 1.7 is 1.2 meters. And we're asked to what is the change in pressure. Now pressure is force over area. However, the area of the water column is the same as the area of the top of the swimmer. So it cancels out. So the increase in pressure is just the increase in force. So we just calculate the force. So the density of seawater is 1030 kilograms per meters cubed. But it's just meters squared because we're not only working on like it above it. So it's 1.2 times 1030 times 9.8 to convert it into weight, or in this case pascals, and then we get 112.8 pascals. As you remember, the unit for pressure is pascals. Now, figure 5. Now for question 5. Figure 7 shows the apparatus a student used to investigate the reflection of light by a plane mirror. The student drew 4 ray diagrams for each angle of instance. The student measured the angle of reflection from each diagram, and table 2 gives the results. And we're showing the apparatus they used and the table of their results. For each angle of instance, the angle of reflection has a range of values. This is caused by an error. What type of error will have caused each angle of reflection to have a range of values? And this is random error. Quick reminder that a random error is one where the difference from the true value is random and you cannot predict in which way it will be different from the true value. And a systematic error is when it's always off from the true value by a certain amount. And we're asked what the student may have done to cause the angle of reflection to have a range of values. And I'm thinking, and the mark scheme agrees, that it's due to the misjudging the position of the center of the ray. For example, like this is the reflected ray. Is it going to be, if the student makes a mistake, they may not measure exactly the center, which would lead to the angles being different. And then we're asked to estimate the uncertainty when the angle of instance is 50 degrees. And how I determine the uncertainty is a range, is half range. So the range is 56 minus 46, and the uncertainty is half the range, which leads to an uncertainty of plus or minus 5 degrees. Then the student concluded that for a plane mirror, the angle of instance is equal to the angle of reflection. Explain whether you agree with this conclusion. Now, if you remember anything, you'll know that the angle of instance is equal to the angle of reflection. So I would often try and argue that the student is correct, and I agree with their conclusion. And the evidence from table 2 I used to do this is the angle of instance is nearly always the same as the angle of reflection, with there often being one result that is exactly the same. For example, for 20, the test 3 is 20 degrees. For 30 degrees, test 4 is 30 degrees. And for 40, test 2 is 40 degrees. And we're asked what extra evidence could be collected to support the student's conclusion. And results could be collected for angles of instance not yet measured, such as 10 or 60 degrees. And asked to state one change the student should make to the apparatus if he wants to use the same method to investigate diffuse reflection. And this is replace the mirror with an irregular reflecting surface, such as paper. Okay, moving on to question 6. Figure 8 shows a boat floating on the sea. The boat is stationary. Figure 9 shows part of the three-body diagram for the boat, and we're asked to complete the three-body diagram for the boat. The boat being stationary means there's no resultant force on the boat, which means all forces are balanced and cancel out. Now there's no horizontal forces on the boat to cancel out, however there is a large weight force downwards which we would need to cancel out. And in this case it cancels out with upthrust, with the upthrust force being equal to the weight, allowing it to be stationary. And you do this by drawing an equal length arrow to the weight and simply labeling it up thrust. Then we're asked to calculate the mass of the boat, and we're given the scale that 1 centimeter equals 5 kilonewtons. So if you have a ruler and you measure the weight, it's 5 centimeters, and that means the weight is 25 kilonewtons or 25,000 newtons. And we simply do the formula weight equals mass times gravitational field strength. Mass equals 25,000 divided by 9.8, and you get a mass of 2,551. And then for question 3.6, when the boat propeller pushes water backwards, the boat moves forwards. The force on the water causes equal and opposite force to act on the boat. What law is this an example of? And of course, it's an example of Newton's third law. Now then, moving on to 6.4. Figure 10 shows the boat towing a small dinghy. The tension force in the tow rope causes a horizontal force forwards and a vertical force upwards on the dinghy, and we're given the values of the two forces. Now, you may be asking what we actually need to do with this information. Well, on the next page, figure 11 shows a grid. Draw a vector diagram to determine the magnitude of the tension force and the direction of the force this causes on the dinghy. Now what you need to do is you just need to draw a simple vector diagram. I made it so one box, or like 2 centimeters, I believe, that's the length of the grid, is equal to 25 newtons. So I go 6 across and 2 up, because 150 divided by 25 is 6, 50 divided by 25 is 2. And I simply draw a line connecting the two endpoints. Obviously use a ruler, draw it better than me, and you get 158 newtons, or you can simply use Pythag, and then you simply measure the angle and get 19 degrees. Then, moving on to question 7. A student used a simple transformer to investigate how the number of turns on the secondary coil affects the potential difference across the secondary coil. The student kept the potential difference across the primary coil fixed at 2 volts. Figure 12 shows the results collected by the student, and was asked to suggest one possible reason for this anonymous result. And the reason I came up with is that there may have been too few turns on the secondary coil. Then, 7.2. The transformer changes from being a step-up to a step-down transformer. How can you tell from figure 12 that this happens? As the PD goes from decreasing before 20 turns to increasing after 20 turns. Now, as it said earlier on, the potential difference across the primary coil is fixed at 2 volts, which means before 2 volts, like, it's a step-down transformer, and after 2 volts, it's a step-up transformer. And for 7.3, asked, how does the amount of infrared radiation emitted by the nails change when the power supply is switched on? And it increases until the nails reach a constant temperature. And then 7.4 is actually a rather hard question. We're asked to calculate the current from the power supply used to provide a power output of 336 watts. Now what we need here is we just need to get all the formulas related down. I'd write all the formulas out first, and then I'd start plugging stuff in and see where you can go with it. So the first formula is that primary turns divided by secondary turns equals primary voltage divided by secondary voltage. And because we have the primary and secondary turns and the secondary voltage, we can rearrange it to get a primary voltage of 280 volts. And then we just use the formula P equals IV, 336 equals 1.75 times IS, and we get a current of 1.2 amps. Now, moving on to question 8. A satellite is in a circular orbit around the Earth. Figure 14 shows the velocity of the satellite at 2 different positions in orbit. I'm asked to explain why the velocity of the satellite changes as it orbits the Earth, and of course, the answer I wrote isn't here because PDFs are evil. Okay, now that my answer's finally where it's supposed to be, the answer is the force of gravity causes the satellite to accelerate towards Earth, with this acceleration causing a change in direction, with the velocity changing because direction changes. So how it works is there's always constantly a force towards the center of the Earth that changes the velocity. So the velocity changes like constantly as it goes round, constantly pulling towards Earth, until it's at this position, and it just repeats and it's in a circular orbit around the Earth. Moving on to 8.2. A satellite orbits 300 kilometers above the Earth's surface at a speed of 7.73 kilometers per second. Calculate how many complete orbits of the Earth the satellite will make in 24 hours. I did not do this the way the mark scheme did, but I believe my way is better. So, 300 kilometers above the Earth, you just go up and across, and you get an orbit length of 42,100. The speed is 7.73 kilometers per second. So you times that by 60 to get it in kilometers per minute, times by 60 again to get it in kilometers per hour, and then times it by 24 to get kilometers per day. And then you simply divide the value for kilometers per day by the length of orbit to get orbits per day, and you get 15.86 orbits per day. However, it's asking specifically how many complete orbits there are. So you instead of just rounding to 16, you truncate it to 15 and you get 15 complete orbits. And then in 1772, an astronomer called J. Bode develops an equation to predict the orbital radii of the planets around the Sun. Table 3 shows the predicted radii and the actual radii. The predicted data can be considered to be accurate, explain why, and this is due to the predicted data being very close to the actual data, like 60 is close to 58, 105 is close to 108, and so on and so forth. J. Bode used his equation to predict the existence of a planet with an orbital radius of 2,940 kilometers. The planet Uranus was discovered in 1781. Uranus has an orbital radius of 2,875 million kilometers. Explain why the discovery of Uranus was important. The discovery of Uranus supported the prediction made by Bode, with the providing evidence that the equation is true. So, not only did the equation match what had already been discovered, it had matched something that had yet to be discovered, further increasing its validity. Now moving on to question 9. Light is usually described as a wave. Light can also be described as a stream of particles, which are called photons. You don't need to know that for this part, but fun fact. Which statement describes a scientific model? And a scientific model is an idea used to explain observations and data. You can eliminate the other two because you really don't use the word guessing in science that often. You often quite describe it as estimating, and a small scale version of a real object isn't true. Okay. 9.2. Why do scientists sometimes have different models, like the wave and particle models of light? And this is due to the two different models may be appropriate in different situations. And for 9.3, sometimes an old scientific model is replaced by a new model. Explain why scientists replace an old scientific model with a new model. Include an example from physics in your answer. There may be new evidence or evidence that cannot be explained using an existing model, with a new model helping to explain this evidence, such as the nuclear model of the atom replacing the plum pudding model of the atom, or heliocentric model of the solar system replacing the Earth-centric model of the solar system. Now 9.4. Some students used water waves in a Whipple tank to model the behavior of light waves. Figure 16 shows what happens to the wave fronts as they pass the boundary between deep water and shallower water. Explain why refraction happens at the boundary between deep water and shallow water. The speed of the water is lower in shallow water, so the edge of the wave front entering the shallow water slows down, but the part of the wave in deeper water continues at a higher speed, leading to a change in direction of the wave fronts. And then 9.5, figure 17 shows the wave fronts traveling parallel to the boundary. And why do they not refract at the boundary? It's because every point on the wave enters the shallow water at the same time, and so every point slows down at the same time, leading to there being no refraction. Now, last question, question 10. Figure 18 represents a straight wire carrying a current. The cross shows that the current is into the plane of the paper. Complete figure 18 to show the magnetic field pattern around the wire, and it's just 3 circles around the wire, and then arrows going around. Then for 10.2, the magnetic flux density 10 centimeters from the wire is 4 microtesla, which is the same as the following as 4 microtesla. And we're just meant to tick one box. Now, going down from the standard thing, it's milli den micro. So it's times 10 to the minus 6, because it's times 10 to the minus 3 for each step, with milli being times 10 to the minus 3. Actually, let me do this. This would be milli Tesla, and this would be milli nanotesla, and this would be centitesla. So it's very important that you remember all your unit prefixes, and this would be microtesla. Anyway, moving on. Last question. Shows a simple electric motor. When there is a current in the coil rotates continuously, and we're asked to explain why. The sides of the coil, which are parallel to the magnet, experience a force. The force causes moments that act in the same direction, which then causes the actual coil to rotate. Each half revolution, the two halves of the split ring commuter swap from one brush to the other, with this keeping the forces in the same direction, allowing the coil to keep rotating. So basically, the sides of the coil experience a force, which causes it to spin. However, when it would get to the other way round, it would then start spinning backwards. However, the split ring commuter means that the current is always constantly going through it in one direction, allowing it to keep rotating. Anyways, that's the end of the video. If you enjoyed this video, make sure to like and subscribe, and I'll see you next time.